Hi, welcome to this video lecture where we will see how to solve the non-homogeneous second-order linear constant coefficients ODEs. We saw in the previous video lectures how to solve this very specific type of ODE when the right-hand side was equal to 0, but now it is not equal to 0, it is non-homogeneous. We will see that it is very easy to solve it, and we will prove it, how to solve it, using this theorem we have here, which is very easy to understand and very easy to prove. Now, let's consider a non-homogeneous second-order linear constant coefficients ODE, like this one, that I will number as number 1. And let YPT denote a particular solution of the ODE 1. And YHT be the general solution of the associated homogeneous ODE, that I will number as 2, that looks like this. It's exactly the same ODE I have here, but instead of having f of t, it is equal to 0. That's why it's called the associated homogeneous ODE. Now, then the general solution of the non-homogeneous ODE we want to solve, the one numbered as 1, is given by the sum of one particular solution of the ODE and the general solution of the homogeneous equation. Now, remember that in the previous video lecture, we were able to solve this type of ODEs, the ones that were homogeneous. So somehow we already know how to find this general solution of the homogeneous case. So if this theorem is true, which we will prove it in the next slide, in order to solve this ODE, which is non-homogeneous, the only thing that remains to be explained, and we will do in this lecture, is how to find one particular solution of the ODE 1. Okay? Okay, so the proof of this theorem is very simple. Remember, it can be very complicated to solve a differential equation, but it's very easy to check if something is a solution. Just plug it into the ODE and see if it verifies it. That's what we will do here. We want to verify if this is a solution of the ODE. So the only thing I'm doing in this proof is plugging into the ODE this function. Of course, the ODE looks like this, and in order to plug in this ODE, this function, I need to know how to compute y prime and y prime prime. I think that is very, very easy. This is just the sum of the functions. So in order to compute y prime prime, this is just, the result of this is just y prime prime p plus y prime prime h. Now, the first derivative of yp plus yh is just y prime p plus y prime h. And yp, the particular solution we are trying to this is incorrect. This should be without the p. Okay, we are trying to prove that this y is solution of this ODE. So we are plugging y prime prime, y prime, and y, which is yp plus yh, into the ODE, okay? Now, if I put together all the terms that involve yp, this comes from this one, and I put together all the terms that come from yh, this comes from this one, okay? I will see that these terms here are equal to 0 because YH is the solution of the homogeneous equation. So I know that YH verifies this. YH is the solution of the ODE when it is homogeneous. So this must be equal to 0 because this is already the ODE. So YH is the solution of the homogeneous, so this is equal to 0. Now, YP, we know that YP is a particular solution of the non-homogeneous ODE. So what we can see here is that I have the ODE substituted at YP. This must be equal to f of t, because I know that YP is a particular solution of the non-homogeneous ODE. So it should be equal to f of t. F of t plus 0 is equal to f of t. So this completes the proof. So, summarizing, in order to solve a non-homogeneous second-order linear constant coefficient ODE, I will just solve the homogeneous equation as we explained it in the previous lecture, and then the only things that remain to be done is to find a particular solution, and this is what we will study now. In this course, we will not explain this method. We will only explain the undetermined coefficients method, and we will see it right now. The method of undetermined coefficients is used to find a particular solution of this type of ODEs. And now it's going to be very important, f of t. In fact, I will write here like an alert sign, very important. This method can only be used when f of t has something called a finite family of derivatives. So this method cannot be used always, okay? It really needs f of t to be of a specific type. We will see now what we mean with a finite family of derivatives. Here we have a table that represents all the possible functions that have a finite family of derivatives. There's no other function that has a finite family derivative that is not in this table, okay? Now let's try to understand the meaning of finite family of derivatives. I will put you an example so you will really understand. Let's start assuming that f of t is a polynomial like t squared. Okay, which are the derivatives of this function? F prime is 2t, f prime prime is equal to 2, and any other derivative is equal to 0 for all n greater or equal than 3, the derivative is 0. So I can write any function here and the function itself, so the function and its derivatives, they can be written as a linear combination of these functions I'm writing here. So there is a finite, there are only 3 functions here, so it's finite. A finite family of functions allows us to write any of the derivatives and the function itself. For example, if I want to write f of t, which is t squared, I will do the following linear combination: 0 times 1 plus 0 times t plus 0 plus 1 t squared. So I will use these coefficients to make a linear combination of these functions, and I can reproduce the function t squared. Or for example, f prime t, which is equal to 2t, can be reproduced by doing a linear combination of the functions here. For example, 0 times 1 plus 2 times t plus 0 times t squared. And we could do the same with f prime prime, and of course with any of the other derivatives, just selecting 0 coefficients everywhere to get this 0. So what's the meaning of a finite family of derivatives? It means that there is a basis with a finite number of elements that allows us to write any derivative of the function and the function itself, just doing linear combinations of the functions here in the basis. Let me show you another example, okay? For example, we can use a cosinus function and see what happens, okay? Let's say that f of t is a cosinus of kt. K can be any real number you want, okay? That doesn't matter. Who is going to be f prime? F prime t is minus k sinus of kt, yeah? And who is f prime prime of t? Well, that's minus k squared cosinus of kt. And I could go on, but basically what we can see here is that the functions that appear are the cosinus and the sinus functions alternatively. And yes, I see here that there's a constant factor in front of them, but this is just a constant value. It doesn't depend on time. That doesn't depend on t. So I can use a finite family of functions given by the cosinus and the sinus of kt. And just by doing linear combinations of these two functions, I can write any of the infinite derivatives that we have here. Yeah? Because I can just use this as the constant to make the linear combination. For example, f prime prime t can be reproduced using minus k squared as constant, as the constant that multiplies the cosinus here, plus 0 times the sinus function. So this is a linear combination of cosinus and sinus that allows us to rewrite this function. So I hope it's clear the idea of finite family of derivatives. The finite means that the number of functions we have in the basis is finite. Okay? Now, the only functions that have a finite family of derivatives are polynomials, as we can see here, polynomials, exponentials, sinus, and cosinus. And also we can have the sum of any of these previous functions we have here, or the product of any of the functions we have here. Let me show you an example where we have, for example, the sum of these two of these functions, okay? So let's say I have as f of t the exponential plus a polynomial, okay? Now, what's the basis? Or how can I compute the basis? It's very easy. If I have the sum of the two of these functions, its basis is just the union of the basis of g1 and g2. So, let me do this small table here, okay? If f of t is the exponential, I know that the basis of the exponential is the exponential itself, because the derivative of the exponential is itself. And when I have polynomial, the basis is 1t and up to t squared. Now, if I have the sum of these two functions, then its basis is the union of these two bases. So remember that the union of these two bases is just to put all them together. Okay? In case we have the product, let's say I have the product of an exponential times a polynomial, then the basis is given by the product of the members of the two families. So I will use the basis of the exponential, and I will do the cross product with the basis of the polynomial. So that's the exponential times 1, the exponential times t, and the exponential times t squared. And that's the basis for the product of two of these functions, okay? So these are the only types of f of t we can deal with when using the undetermined coefficients method that we will see right now, okay? Here you have some examples. You can try to do it at home and be sure you understand how the bases are derived, that you really understand how to write down the basis for the different functions. This is important, okay? So I will let you do that at home. Now, what's the method of undetermined coefficient? What's the main idea? It relies a lot on f of t. Remember, it's very important that f of t has a finite family of derivatives. I was reading this in this other notation for the basis. It really means the same thing. It means that it is a basis, okay? And the undetermined coefficients method tries to find a particular solution that is pretty similar to f of t. And what's the meaning of pretty similar? Well, it tries to find a particular solution that can be written as a linear combination of the elements in the basis of f of t. And these coefficients of this linear combination are right now undetermined. These coefficients here, you don't know the value of them. That's why the method is called undetermined coefficients, because you propose to find a particular solution that is pretty similar to f of t in the sense that it can be written as a linear combination of the function in its f of t basis. And you introduce these coefficients that are undetermined, and you need to find out their value in order to find out who is yp. So let me show you this with an example, okay? I will start with this example here, which also has a little bit of theory associated, so keep an eye on this example, it's very important. We want to find the general solution of this ODE. The first thing is to make sure it is second order, it's linear, it has constant coefficient, and it's non-homogeneous, okay? Now, as this is non-homogeneous, we know that one way to solve it, or the way to solve it, is that the solution, the general solution, is the sum of a particular solution of this ODE plus the general solution of the homogeneous equation. And we already know how to compute this guy because this is the solution of the homogeneous ODE. So the case where we are just neglecting this term here and make it 0, okay? And in order to solve the homogeneous equation, we just write the characteristic equation, we solve for S, and we found that in this case, we are in case 1, we have two different real solutions, and the general homogeneous solution looks like this, okay? This is pretty easy. Now, what about finding yp? That's what we are interested. In order to find one particular solution of the non-homogeneous ODE, we will use the method of undetermined coefficients. Can it be used? Yes, because the right-hand side is an exponential function times a constant. So it has a finite family of derivatives, okay? And in fact, this is the basis. The basis is just the function exponential of 3t. So initially, and we will see that we have a little bit of trouble, but initially, the method proposed to find a particular solution that is just a linear combination of the elements in the basis. So it will propose to have a constant times the exponential. Now, how do we verify that this is a solution? Just plug this into the ODE. The idea is to plug this yp into the ODE and try to find the value of A that makes this a particular solution of the ODE. So in order to do that, starting from this proposed particular solution, we compute its first derivative and we compute its second derivative. This is pretty simple, yeah? And now, using this, we will plug them into the ODE, which looks like this. But we have a problem, because when we do that, you know, here y prime prime p is this guy, y prime is this guy, and yp is this guy, and this sums out to be 0. And we wanted it to be different from 0. It was a non-homogeneous equation. What happened here? It's impossible. What can we do? Okay, I have decided to do this example because it's the very specific case where one of the homogeneous solutions happens to be f of t. So, if this function here is already a solution of the homogeneous equation, of course, it cannot be at the same time solution of the non-homogeneous. So, what can we do when this happens? If this happens, we will multiply by t the elements in the basis. So, we will try multiplying this by t and checking that t times the exponential is not solution of the homogeneous, which can happen when we solve the characteristic equation and we are in case 2 and these two are equal. In that case, we would have here this, and this would be again solution of the homogeneous, and we need to multiply again by t. And that's it, because of course this will never be solution of the homogeneous, okay? So, in this particular example, we are in case 1, and we only need to multiply it by t once, because t times the exponential is not solution of the homogeneous. So we will try now multiplying by t, okay, this function, okay? Now, we propose yp to be like this, a linear combination of t times the exponential. We compute y prime, we compute y prime prime, we plug it into the differential equation, and now it is solvable. We find this equation here. And we find out that A must be equal to 2. So yp is 2t exponential of 3t. Therefore, the final general solution of the problem is the sum of the homogeneous plus the particular solution we found. Here we have the homogeneous plus the particular solution we found. This example is the worst case, okay? It is when we have that f of t that appears here, okay? It has a family, a finite family of derivative, and when we write the basis here, it happens that some functions here in the basis are already solution of the homogeneous. Of course, it doesn't make any sense to try to find that it is also solution of the non-homogeneous. So in that case, we will multiply by t. Let me show you another example, which I think it's easier, which is this one, okay? Here, we want to use the method of undetermined coefficients in order to solve this ODE, which is second-order linear constant coefficients and non-homogeneous, okay? Remember that in order to solve it, yt, the general solution of this ODE, is the sum of the general solution of the homogeneous case plus a particular solution of this non-homogeneous ODE. Remember that it's very, very easy to find this guy because it's the solution of the homogeneous ODE, and we know that that's very easy. We will just write down the characteristic equation, which is this one here, solve it, and find out the values of S that allows us to find the general solution of the homogeneous associated ODE, okay? Now, how do we find the particular solution? In order to find the particular solution, we will use the method of undetermined coefficients. Can we use it? Yes, because the right-hand side, f of t, in this case is a polynomial, so it has a finite family of derivatives, and we will propose to find a particular solution that is just a linear combination of the elements in the basis. Wait a moment! Is there some of these guys here? Is one of these guys solution of the non-homogeneous? No. The solution of the homogeneous are both exponential functions, so we will not have the problem we had in the previous example. We do not need to multiply by t anything in this problem. We will propose to find a particular solution that looks like this. So now we will just note here that I have some coefficients, A, B, and C, that right now are undetermined coefficients. I do not know their value. That's why the method is called undetermined coefficients. But I will find their value. How? Plugging into the ODE this proposed particular solution and finding out the values of A, B, and C. Let's do that. This is the proposed particular solution. From this we compute y prime and we compute y prime prime. That's pretty easy. They are just derivatives of polynomials. And then we plug them into the ODE. See here, y prime prime p is this guy to see here. Then, for example, 3 times y prime p is this guy here, p plus 2ct. And then, for example, minus 10 yp. Yp is this thing here that we written here. Okay, now we will put together all the terms that do not involve t. We will put together all the terms that multiply t, and we will put together all the terms that multiply by t squared. So you can check, but the only thing we did from here to here is to rewrite in this manner, okay? Now, of course, when I have here that this should be equal to 5t squared, because that's the ODE I want to solve, this thing should be equal to 5t squared. Of course, this is the same as saying that there is no term multiplying t and there is no constant term. These are zeros, yeah? So this thing here is constant. It should be equal to 0. This thing here is multiplying t, and the term that multiplies t is 0, so this should be 0. And the term that multiplies t squared should be equal to 5. So at the end, we have this linear system of equations that comes from these 1, 2, and 3 equations here. We solve it and we find the value of the undetermined coefficients. So finally, the particular solution we were looking for, which had this form, Now we know the values of A, B, C that we found here, and we can plug them and obtain the particular solution. Now, finally, to summarize, the general solution of the ODE is the sum of the general solution of the homogeneous ODE and the particular solution we computed with the method of undetermined coefficients. That's it for today. Thank you very much. Bye-bye.